Welcome to Computer Architecture. In this mini lecture, we are going to talk about how we can deal with large constants, especially when dealing with memory address in MIPS. The first thing to remind you is that remember, when we make good design, it will require good trade-off, good compromise. And one of the design choice by MIPS is that to enforce all the instruction to be 32 bits long. But the problem is that sometimes we need to have a constant or need to have address that is 32 bits. But you already have some operation code or some register like positions. So how can we get this 32 bits? And that's the topic of this mini lecture. The first instruction we can use is called low upper immediate. It's that the register S0, and then this is the bit, the numbers that you want to put in. So the pseudocode of this instruction is that first I'm going to convert 255 into binary. And then I'm going to copy the 16-bit binary to upper 16-bit of the register, which is in S0 in this example. So if you do the translation, the machine language is like this. And then to help you is that the first field is operation code. The second field is the register. Then the third field is also the register, like the source and destination. And then finally, we are going to have a 16-bit immediate value. Okay. Then after completing this instruction, your register T0 will look like this because only the value is copied into the upper 16-bit. So all the lower 16-bit are all zeros. Obviously, this is not done yet because we want to have 32-bit address. What do we do next? And here is that we need to use another instructions to load the lower 16-bit. In this example, it's ORI S0 because we are going to copy something into the same register, and then that this is just some number we want to copy into the lower 16-bit. And what is ORI? It's all immediate. That's why we can include the constant here. And then there's another type of instruction called J-type, where we have 16-bit of operation field and 26 bits of address field. That's one of the simplest instruction, and that gives you very simple addressing. So the instruction very simple, just J and then your memory address. So that's just tell you go to location 10,000 in this example. Now let's look in more detail how do we represent address when we do branches and when we do jumps. So remember what J-type, it's like this, and then your machine code, just like your operation code, which is 2, and then your address, very simple. And then if you do branch, here's the example of BNE S0 S1 exit. And if you recall, the idea of this instruction is that go to the flag exit if the value inside register S0 is not equal to the value of register inside S1. Okay, and then if you translate that into machine code, it's the same thing, up code, and then the first register, second register, and then exit tell you the memory address. In this case, you only get 16-bit, okay? But if you only have 16-bit, obviously that's not very ideal because how big can your program be? Because remember, your program is limited by the memory address that you can specify, right? So in this case, just a 2 to the power of 16. So that's not good if we want to write a large program. And now, look in more detail in MIPS. What we can do is that the program counter, the memory address that we want to jump to, actually it's a sum of value inside register plus your branch address that you specify as the 16-bit value, 16-bit constant here. And then this is also called PC relative addressing. Then in this case, exercise for you is to figure out that how big can your program be with this kind of design. Right? Then now let's look in more detail. Remember, all MIPS instructions are 4 bytes long, 32 bits, okay? And then the PC relative addressing refer to the number of words to the next instruction, right? And then it's relative because everything is relative to your program counter. So the 16-bit field can branch 4 times as far because you have like 2 bits that's that you can specify. So as a relative word address. And then remember that in the J type of operation, J type of instruction, we have 26-bit, and then that's actually is used as a 28-bit address. So now for jump is that remember we have this 28-bit address, but like the MIPS inside the program counter is 32 bits. So we somehow need to have 4 more bits somewhere. And this design actually is very simple. When we call a jump instruction, it only replaces the lower 28 bits of the PC. Now to sum up, if you look at all the prior mini lectures, we talk about different addressing modes. And there are 5 of them. The first one is immediate addressing. The second one is register addressing. And these 2 are very simple. The first one means that you specify the address inside your instruction. So that's called immediate. The second one is that your address is stored as a value inside a register. And then the 3, 4, 5 are slightly more complicated. The first one is called base addressing, or sometimes called displacement addressing. The fourth one is PC relative addressing that we just mentioned. Then the final one is pseudo direct addressing. So for the third one is that you have a register, and then the instruction also specify a constant. So you just sum those 2 to specify your address. And for PC relative one is very similar, but now is the first one, the first sum here is from the PC. Then for pseudo direct is that you specify 26-bit constant in your instruction, and then you just concatenate with whatever you have inside your PC's upper bit. Because remember, for jump instruction, you only replace the lower 26-bit. And then that's all the addressing mode that you are going to deal with inside MIPS design. In summary, we talk about operations with immediate field, and in particular, this is very useful for specifying address.